So good afternoon all again. So today our topic will be on a fully polynomial time approximation scheme, the last topic of the syllabus. So okay, so you already know that what is the definition of a fully polynomial time approximation scheme. Uh, so these are the algorithms, approximation algorithms. Uh, uh, these are, polynomial time approximation algorithms, which in which the computational time complexity follows a polynomial both in the problem instance n and 1 by epsilon, where epsilon is some bound positive constant. Okay, so in this type of algorithms, you see approximation algorithms are designed and based on the problem statement given. So there is no hard and fast rule. There will be some traditional algorithm, some technique. Okay, so which will solve almost all the problem statements. So that is not true. So based on the problem statement, you have to design the approximation algorithm. There is no hard and fast rule, but still, while solving many problems, lot of problems, people have come up to this theme fact that there are three popular methods or techniques. So there are three popular techniques which are used used in FPS. So this techniques usually solve optimization problems. Okay, are modeled their models are like an optimization problem. So let's say capital X O equal to argument of max of summation I x I is equal to, okay, and this model is having some heuristic objective to summation over less than equal to some bj. 1 to n, here we have 1, okay, here So this is a generalized model of an optimization problem, and you can see that this is almost looking like, okay, another thing we have here belongs to, okay. So this is more or less, if it is wixi, then and it is less than equal to m, this is absent, then it becomes a model of 0 by 1, 0 1 knapsack problem. And so that means this model can be viewed as a generalized, similar to generalized 0 1 knapsack problem, capacity J, J 1 less than equal to J. So now here, so if optimization, this optimization problem can have a deterministic algorithm designed using dynamic programming. And so in that case, let the number of solutions, okay, uh, uh, solutions, number of noted as is denoted as, let's say, S I, S I for the variables 1, okay. So I number of x values variables, if you consider, then let the number of feasible solutions, all the feasible solutions, is denoted by si. Okay. So where each xi can have either value 0 or value 1. So you can say that in the next line, that si is equal to the power of I. Right? So I hope you can understand this. Okay. So that means in the next line, what we can say that, so if the number of feasible solutions is in the form of 2 to the power of I. That means if you consider Sn, it will be 2 to the power of n. So all these feasible solutions will be checked whether uh, they will belong to the optimal solution set or not, right? So so that means the computational time is in the order of 2 to the power n, clear, right? So clearly the computing time is exponential time function. Okay, this is clear. So this reduced polynomial function, poly polynomial time function. Okay, by applying, because fully polynomial time approximation, the computational time in this kind of approximation scheme must follow a polynomial function of n as well as polynomial function of 1 by epsilon. So, we will take up two very good example and will illustrate, derive that those two problems are can have approximation scheme, uh, okay, which are fully polynomial time. Okay, so it's a very good mathematics you can see over there. So this can be reduced to polynomial time function by applying rounding, interval, partitioning, okay, or separation. So as nothing is mentioned explicitly in the syllabus, so I shall cover one technique, let's say rounding, which is very popular. So rounding technique, and thereby I want to show you two important problems. One is a simple polynomial time approximation scheme. Another is randomized fully polynomial time approximation scheme. For a fully polynomial time, randomized approximation scheme. Okay, so and both are how both of these problems are actually are having APAs, so we can derive that thing. Okay, mathematically. So let's now move on to rounding. Okay. So this technique, what we want to do, start with, okay, problem instance I and transform it to another instance I dash, which is easier to solve, such that solutions to I and I dash are very enough, enough to, so that means close enough means what? Here we have the mathematical model formula. This is f star I minus f dash I. Okay, so this fractional difference, absolute difference between the optimal solution to the problem instance I and the optimal solution to problem instance I dash, this fractional absolute difference must be less than or equals to okay, so where epsilon is some positive constant. So this is known as epsilon approximation algorithm. Okay, at this moment these are approximate. It is looking like epsilon approximation algorithm. Okay, the I dash is the solution, the algorithm is epsilon approximation algorithm. Uh, okay, in terms of f star I and f star I dash. So if I treat that f star I is the exact solution and this is the approximate version of that, then I can call the algorithm which is producing f star I dash, okay, will be called as epsilon approximation algorithm. So I have to uh, mention that. So start with the problem instance. Easier to solve and approximation algorithm A such that this. So where star I comma f star I dash are optimal solutions if star are optimal I and I dash. Okay. So next what we do, in I dash we have uh, transformed objective um, earlier what we have said that or not? Yes. So let's say this is the model of to the problem instance I, summation over pixi, maximizing the profit function, objective function, summation over pixi, and that is the model of the objective function to the problem instance I. Okay, assuming that, and then in I dash, a new problem instance I dash. So the transform objective function becomes, say, max of summation over some q, not p, but qi. I belongs to n. Okay. Right. Now algorithm A to determine wise such that this is true f star I minus f star I dash by f star I, this absolute value is less than equal to epsilon, where epsilon is some positive constant, and summation over, okay, and the computational time of that algorithm must be following a polynomial time function of n and 1 by epsilon. Okay, so the computational time is nothing but, okay, the number of feasible solutions, that is S of the, if Si is the set of all the feasible solutions, then cardinality of Si set is actually giving us the computational time, okay, estimate of computational time, measure of computational time to 1 to n. So this computational time, this must be following some, it should be order of some n comma 1 by epsilon. So value of n comma 1 by n comma by epsilon thing we have to prove. So if this is possible, that this second condition is possible, then that algorithm A then the algorithm A polytime scheme. Okay, and we have two popular examples to illustrate this. So we have two just popular examples to uh, them as problem is, okay, generalized by knapsack problem or the optimization problem. So let's say dot one. So let's give the name to this model. Okay. So, and the second one is fully polytime randomized approximation scheme to solve DNF-Counting using, we have discussed earlier DNF-Counting Monte Carlo, so we can use that knowledge over here. Okay. So now let's go for it. Okay. So we know that DNF formula, okay, as follows. Let's say of uh, 1 x2 equal to or of of I equal to 1 to plus where Ci equal to and of Ig. This is let's see. Okay, let's say k number of clause we have. Each clause we have k number of literals. Okay. So Lij are the literals. J either xi xi bar or not of xi. Okay. So this is the model formula, okay, where okay. So if we have we consider all n variables, so then if we consider all n variables, then some number of that can satisfy DNF DNF formula will be exponential function. Okay, so uh, I mean 2 to the power n. right? That is also 2 to the power n, and that is exponential. That means computing time using deterministic algorithm, you are trying all the assignments and verifying that those assignments are satisfying the DNF formula or not. So computing time using a deterministic greedy algorithm, okay, will, will be an exponential. Okay. So to reduce this, we can take the advantage of randomized algorithm. So the randomized algorithm to the problem, to the above problem, to the problem of DNF counting, IV problem instance, okay, problem instance, um, is the number of satisfying assignments, and Y is that, okay, we can use uh, if star I, okay, forget about this thing, we will use traditional notation, problem instance. Then we have I. So this is the estimate, the number of satisfying assignments to the problem instance I by the randomized algorithm A. Okay, so this is lying within a range given by this 1 plus epsilon into A star I. So F star I is the exact number of, actual number of assignments, that is the DNF counting. So F star I is the DNF counting. Okay, the exact number of satisfying assignments is equal to, this is minus epsilon star where F I and F star I, sorry, F not bar I, okay, exact DNF counting and approximate okay. So if we can have this result, Okay, so 1 minus epsilon f star I less than equal to f or I less than equal to 1 plus epsilon f star I. Okay, so epsilon is some positive constant belongs to 0 to 1. Okay, so let me see 1. So we claim that if the condition dot 1 is satisfied, then A this algorithm A can run in a polynomial time complexity function of problem instance n and 1 by epsilon, where epsilon belongs to 0 to 1. Okay, so this is our claim and we will go for it. Okay. So as A is an is a randomized algorithm. Okay. Let probability of failure be delta such that delta belongs to probability delta 1. Okay, 0 to 1. And to this, then probability of success 1 minus delta. Okay, so then we can come up to this result. Okay, then we come up to that result that in condition C dot 1 of okay, probability of this event. Okay, the probability that the approximate DNF counting f bar I will belong to this range 1 minus epsilon times exact DNF counting to 1 pi plus epsilon times exact DNF counting. So probability of achieving this will be, will be, that means it's a success. So this is the condition. So if this condition is true, then I will say that we can find an algorithm A which is APS. Okay, so and we will have some success, and the success probability is 1 minus delta. That means this probability has to be 1 minus delta or more than 1 minus delta. So it is greater than or equal to 1 minus delta. Okay, so this is the modified version of the condition, that is C dot. So here where log of log of 1 by delta okay. Okay, so here we can say that if the condition C dot 2 is satisfied for every such delta, I'm not writing here the function, this delta, okay, delta in the delta, then randomized FPS. Okay, so this is our claim. So the modified claim. So our modified claim is the condition C2 is satisfied, then for every such delta chosen, we will have an algorithm which is randomized FPS. So next, it's already 1:41. So are we having another 5 to 10 minutes, because we will go to the derivation part. In the time we start. In Monte Carlo method, let's consider, okay, universal set, set of subset of interests. Okay, so G is a subset of U, so I'm not mentioning, you know that how to write mathematically, so that's fine. So and in V, the number of trials of number of trials and total trials respectively in, okay, so then we can say that using Monte Carlo, that is uh, the number of elements in G, which is the subset of interest, okay, means the approximate version of counting, approximate counting, equal to the probability of getting success, which is given by a good measure is by times uh, of, okay, so as per Monte Carlo. So this is Monte Carlo based counting. Okay. Now our claim is whether we can get an algorithm which is a randomized FPAS. So let's go for it. We have to prove that, if that condition is satisfied, this condition C2 is satisfied, uh, the computational time will follow a polynomial time function of problem instance n, uh, 1 by epsilon and log of 1 by delta in this case. Okay. Okay. Let already we have assumed that let's compute the estimate, okay, estimate of the number of trials, total number of trials required randomized algorithm A to produce good approximation, that is output reasonably good success probability. So in doing that, let's take some variables or notation. So number of successes in n trials, okay, so we can equal to say y, okay, so then we can say that probability of G, let's say bar, that is the estimate of G denoted by this cardinality of G hat or G bar, okay, estimate is given by y by n into u. So here s is y. So y by n into, okay, we have now what is u, y. We have this result, the expectation of y is expectation of means y1 plus, okay, means summation of y, summation of yi, 1 to n, just oh, summation of yi. So this is nothing but yi will be either equal to 1 or 0. So in that case it is n times expectation of, okay. So in the next line, let be row times n. So where row is and prove that this is equal to g by mod. Okay, so now using the condition 2, what we have, probability of minus epsilon star approximate version, okay. So in our case, g is the estimate and g is the subset of interest. So g is the exact counting, okay, and g dash is the approximate counting. So g less than or equal to g, so that in the next line, oh sorry, this probability is equal to probability of probability of 1 minus this. Here we are replacing this is, you can see, mod g equal to rho into mod u. So rho mod of u. Similarly here do all of you in the next one. Okay, so here what you see, replace this g hat. Okay, so replace that g hat by u by n into y is summation over, okay, so n into summation yi. So in the next line, you can write that. So mod u get cancelled out, okay, and we can multiply the inequality with by n, and we come up to this result. So here this is okay. So next, what we have in the next line, probability of uh, okay. So see this right hand inequality less than equal to 1 plus epsilon rho n. So here you have rho n plus epsilon rho n. Okay, so this is simply, you know, y, summation over yi is y, so y minus rho n, okay, less than equal to epsilon rho n. So this is nothing but probability, and similarly from this left hand side inequality we will have rho n minus epsilon rho n is less than equal to y, so y minus rho n is greater than equal to epsilon rho n. So that means combining them, you can write this summation over summation over yi 1 to n okay minus rho n, almost done, শেষ হয়ে আসছে। ছোট হয়ে গেল। Mod of this is less than or equal to epsilon rho, very good form of the formula we are getting, okay, it's a handy formula, form of the expression, okay. So probability that y minus rho n, so in the next line we can simplify this form of the inequality, that is equal to probability of y minus rho n less than or equal to epsilon rho Right. Okay. Okay. So this is the probability that an approximated counting lies in this event. Means this event is representing a success event. Okay. So its complementary failure event is complementary complementary failure event. So event is represented represented here we want to write that this is success event. Okay, this is representing success event. So here we may have that probability of mod this is greater than equal to epsilon rho n. So mod of 1 minus rho n is greater than equal to epsilon rho. Okay, so this is the failure probability. Okay, and we have a very standard result. Very standard result. This is not in your syllabus, just for information. And using result of Charnoff bound, okay, which is saying that what is Charnoff bound? Charnoff bound is probability of this form mod of x minus let's say mu is equal to okay some times mu delta times mu. Okay, so probability of this model mod of x minus mu greater than equal to delta mu. So this is less than or equal to okay 2 to the power okay minus delta square mu by 3 delta square next mu okay, so minus delta square times mu by 3. So this is the bound which is very popular, known as Charnoff bound. We are not interested to derive this Charnoff bound result. We can use this, and you see in our context we have a similar structure. This is y minus rho n greater than equal to some delta n, right? So here delta is epsilon rho. Sorry, rho n is the mu and epsilon is the delta. That means this probability will have this Charnoff bound less than equal to 2 to the power minus delta square mu by 3, where delta in this case epsilon and mu is rho n. So using this standard result of Charnoff bound, we can have this probability bound for this probability, which is failure probability. Okay, so very important result we are going through. So here we have probability, the failure probability. So this is failure probability of an outcome, that is probability of mod of y minus rho n. Okay, very classical thing. Is the probability that this mod will be greater than equal to epsilon rho n. This probability will have a lower bound, an upper bound less than equal to 2 Here we have delta is my epsilon. So epsilon square oh sorry good 2 e to the power minus epsilon square into mu by 3, that is rho n by 3. So rho okay, so we have this result. Failure probability is not more than 2 twice exponential minus epsilon square rho n by 3. This is the result. That means success probability will be greater than equal to this one. Okay, so in the next line we can say that so here we have the success probability. Success probability is this is more than or equals to this. Okay, so our job is to increase the success probability and decrease the failure probability. So the problem is how can we increase this success probability? Okay, so let's do this probability of this. So we have to estimate the n, right? So from here, what we have, therefore, let given a failure probability, means you will be given a problem. Okay, there you have to find the approximated version of DNF counting. Obviously you will have some error probability or failure probability, but you are also told that whatever output approximate DNF counting you are generating, that must be within the given failure probability. That must be less than or equal to the given failure probability. And let's say that failure probability is, let's say, delta. Okay, let's say we are given that failure probability must be delta, means our failure probability must be less than or equal to delta. Okay, so if I do this, so let we are given a failure probability delta, then we have this failure probability is equal to delta. So this 2 times that expression is equal to delta. Okay. So in the next line, you can apply exponential in the both log in both side, and to come up to an expression. After rearranging, you can, so I am not investing some more time, you can do this. So n will be equal to, after rearranging the terms, n will be equal to 3 by epsilon square log okay. So 2 by delta, where delta is the failure probability. So the number of trials, this is the total number of trials, which is formulated as 3 by epsilon square rho. Epsilon is 0 to 1, rho is it is defined over here, mod g by u, the exact DNF counting by this, okay, or expectation of yi, so log of 2 by delta. So if the failure probability is low, Okay, then automatically 2 by delta will increase and eventually n will increase. Okay, so from here what we can say, so n is the measure of computing time of A plus A computing time of A, a polynomial function log, so a poly time function of 1 by delta. In this case is a polynomial time function, and that is the function of 1 by delta. Okay, 1 by epsilon and also n, so proportional to n. So next what we are having, thus that we prove that, okay, if condition c dot 2 satisfied, then DNF counting will have a randomized algorithm follows a computing time function okay. DNF counting will have a, okay, so algorithm that follows a computing time function poly of n comma 1 by epsilon please excuse me. We have log delta, but delta is the failure probability, and it is 1 by epsilon. Here it is. Okay, so poised and this completes our discussion. So if you have any queries, you can ask me. Okay, so very advanced topic we have discussed today. One example we have done. Uh, let's see if it is possible tomorrow to cover the other example. Okay, so if you have any question, you can ask me. Okay. I recommend all of you who are going for module 5 at least, so please writing the theorems and their proofs. Okay, the proofs are very logical, and it's very difficult to understand all the thing and keep in mind, keep memorizing all the thing. Okay, so if you practice by writing the proofs, then you can uh, more doubts will come, and ask me doubt, I will clear. Okay. Okay, so we can stop recording here.